All right, so conservation of energy, basically, we're going to talk about total amount of energy in the universe is pretty much constant, which means it's not going to be, excess energy given by like other form, right? Or it's not going to get lost. So total energy in the universe is constant. In our physics, we're going to just talk about a system, right? And how much the energy possesses within that system. Well, that energy that system possesses will not gain or lose energy. All right. Now, there are two forces that we're going to be talking about, and that's conservative force and non conservative forces. And this is nothing to do with politics. Okay. Of course, conservative forces, we're going to label it with red, right? And non conservative forces, or the liberal forces, we're going to do it blue. All right. Now, conservative forces basically deals with forces that has to do with locations. Okay. So a force that is conservative, if work done by force on an object only depends on the endpoints. Okay. So what forces, right, depends on endpoints? Well, we know gravity pretty much depends on where you start and where you end up, right? How high it gets or how low it gets, so on. So gravity is a form of conservative force, okay? And so is spring, right? Spring is another conservative force because it depends on how much it is stretched or compressed, okay? And this force is path independent. It doesn't matter, okay, which path it takes to change its position. It just concerns about where it starts and where it ends up, okay? Now, the non-conservative force or force something does work, but you cannot get that work back into the system, okay? So, for example, work done by friction, okay? Work done by friction, once work is done by friction, what happens? That work done by friction converts into thermal energy and it heats up. Now, when it heats up, you don't really like lose energy. It just dissipates throughout the universe and you cannot get that energy back into the system to do work again. That's why it's not conserved, right? Because the total amount of energy is still the same, but it has converted into thermal energy. And thermal energy will not be able to be put back into the system to do the work back. Okay? And other applied forces. So when you push something along the thing, you cannot get that push back because the push is already spent, right? So applied forces, okay, are also non-conservative forces. Okay? So if we were to look at like a gravitational and spring forces, okay, we already talked about spring forces already from last chapter, right? So here, work done by spring is integral of, right, F spring, which is the Hooke's law, right, which is negative kx dot dx. So when we integrate negative kx dx, this is pretty easy, right? We're going to get negative, right? kx squared over 2. Evaluate that from x1 to x2, right? So x1 can be the initial and x2 can be the final. So when we evaluate this, this becomes 1 half kx2 squared minus, right, 1 half kx1 squared with the negative factored out. Okay, so this is work done by spring. Work done by gravity, of course, Fg is constant force. All you have to do is just dot it with whatever the displacement, right? So mg dot delta y would be my work done by gravitational force. Okay? So these are conservative forces that we should be familiar with. Now the work done by frictional force depends on the path. And when it depends on the path, it is non-conservative force. Okay? So work done by friction is friction dot delta x. Okay? So if we were to look at this gravitation a little more, okay? Let's say, here is our ground. Right? This is our ground. And here is our, let's say, y initial, right? This is our y initial. And then let's say here is like our y final. Right? And let's say we start here, and then we move, like here. Right? So this is when we move. So this here is my delta y. And then we'll continue to move from here to here, and then maybe we go all the way to here, and then to here, and then to here, and then here, and then all the way back to the original point. Okay? Well, it doesn't matter where you start, right? Delta y is the only thing that matters, right? Because wherever you start, we're going to consider that to be our initial reference point, right? And then wherever we ended up is the final position, and then the change in that position in the vertical direction is what we're really concerned about. We're not worried about, So where do we set our zero? Do we set our zero at the ground level, or at the y initial level, or all the way down to like the basement level? It doesn't really matter. It's up to you. Right? So if we actually start at any position and then we make a complete circle loop out of this, right? Complete loop and end up at exactly where we started, right? Our work done by Fg then is 0 because our change in position is 0. Okay? So okay? Or if you want, if closed loop integral of f dot ds is 0, right? Then f is conservative. Okay? You'll see this more in E&M, okay, for next year for those of you who are taking AP2. Okay? So this is integral of closed loop. So it's very important to understand, right, the reference point, where it starts and where it ends up. The potential energy, or simply the work done by, conservative force at one single location really doesn't mean anything, right? Because you could just arbitrarily assign whatever the height it is, and it doesn't really mean anything. You could make this into 0 and make this into 100, right? Or you could make this 0 and then make this like 1000. It doesn't really mean anything unless you compare it with somewhere, okay? All right, so now that we have these two different works, we have work done by conservative force and work done by non-conservative force, we can now then say the total work done can be broken up into two different work done by two different forces. So our net work now has new definition. Our net work can be combination of work done by non-conservative force plus work done by conservative force. Okay? And that net work is equal to now change in kinetic energy. Okay? So this here is now our new net work. Okay? And work done by non-conservative force, of course we know it is frictional force, right? And or apply force, right? Okay. And work done by the conservative force is spring force, right? And or right, gravitation, right? So gravity or gravitational force, okay, is equal to now change in kinetic energy. And of course, this combination of this is my net force. Okay. Alrighty. Any questions so far? All right, good. So, how does potential energy and energy function, right, work out? Well, we know the kinetic energy equation from last chapter. The kinetic energy is energy due to motion, right? And kinetic energy is equal to 1/2 mv squared. And this v right here is the speed, right? Doesn't really care about the direction because if you just square it, you're going to get a positive anyway. And energy itself is a scalar quantity, just like work. When you dot two vectors together, you get a scalar. Energy is also a scalar quantity, so it does not have any direction, right? Potential energy is also energy, so it does not have any direction. Now, the potential energy definition is the amount of energy that can potentially be converted into kinetic energy, right? So, potentially be converted into kinetic energy. So, it has potential to do work, right? Because work is changing kinetic energy. So, potential energy is defined as, well, we know kinetic energy is defined as Ke, right? Well, potential energy is defined as Pe. Okay? Now, sometimes Pe is also defined as U. And we'll talk about that more in detail later on because U comes from mathematical representation of potential energy, which is a parabola, especially for spring, right? So this is a mathematical variable for potential energy, okay? And this is a function of either x, right, or function of y, okay, etc. Okay, so this is like a mathematical function. So potential energy can only be specified for conservative forces. Okay? So potential energy can only be specified for conservative forces. It is path independent. Okay? It's path independent. And potential energy is also equal to negative work done by conservative force. Okay? Potential energy is a negative work done by a conservative force. Potential energy is different. Right? Potential energy function is different for different conservative forces. For example, for spring, right? For spring, our potential energy as a function of x is equal to 1/2 kx squared. Okay? And this is for the spring. For gravity, right? For gravity, potential energy is a function of position in y direction. Right? I'm going to say gravity, right? And that is equal to mg y, right? As a function of y, position y. All right, so here's something interesting. This g right here, right, this g, right, always use positive 9.8 meters per second squared. Okay, always use positive 9.8 meters per second squared. However, for the y, right, put in, right, plus or minus, right, for y. Why? 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 Because in this case, if I were to raise something up, right, my positive y would give me positive potential energy, which means that's how much energy it gained. If I lower this thing, it lost potential energy, so you get negative y will give me negative potential energy, which symbolizes loss in energy. Okay? Loss in energy. Therefore, it's very important that you understand that. Okay? All right? Now, the third thing you should know about, I think, you know what, this is also good. Maybe a good idea to just box this off. So, potential energy is energy associated with change in position, and that's very important. Okay? Change in position. So, you can't just talk about just a position really without comparing it to the reference point. Okay? So let's just say we have like a 1 kilogram object, right? And mass of this object is equal to 1 kilograms. And it's going to be going down. Let's say we're going to lower this thing to delta y. And here is my Fg, right? Which is equal to m times g. Right? Now, if we start this at, let's say, 10 meters above the ground, okay? So here, my initial point, my y here, is equal to 10 meters. Then we're going to lower this thing to 0. So here's my y final. So my y final happens to be 0 meters. This is my y initial. Okay? If I were to find my potential energy at the initial position right here, right? So my U of, right, 10 is equal to mgy initial, and that is simply just 1 times 9.8 times positive 10, right? So if you work it out, my U at position 10 meters above the ground happens to be 98 joules. Here, my potential energy at 0 position is equal to mgy final, and that is, right, 1 times 9.8 times 0, and I get my potential energy at 0 position to be 0 joules. Right? So if I want to find out what is my change in potential energy, right, from initial to final, that is really nothing more than initial is, what's my initial right here, 10. My final is 0. So change in potential energy would be UF minus UI, right? UF is U at 0 minus U at 10. So the change in potential energy from initial to final, this is going down, by the way, right? Will be 0 minus 98, which is just negative 98 joules. Okay? Now, how much difference is that if I were to make these values different? For example, let's say instead of 0 here, I call this here as my y final, and that is, let's say, 10,000 meters. And my y initial, instead of 10 meters, what if my y initial was 10,010 meters? Right? How much does it really change? Well, as far as the potential energy at each location is concerned, it's huge difference. However, the change in potential energy may not be the same. I mean, may exactly be the same, right? So U at 10,010, right, is equal to just 1 times 9.8 times 10,010, right? And that comes out to 98,098 joules. And similarly, if we were to do, right, U at 10,000 is same as 1 times 9.8 times 10,000. So U at 10,000 is equal to 98,000 joules. So if I want to look for my change in potential energy from initial to final, that is UF minus UI, right? And that is U at 10,000 minus U at 10,010. Therefore, that is simply 98,000 minus 98,098, and we still get the exact same amount of change in potential energy of negative 98 joules. So the individual potential energy, right? So individual potential energy values, right, have no physical meaning, right? So one must compare it to a reference point, right? Right? Therefore, delta U only has meaning. Running out of room, sorry. Okay? I mean, this by itself, I mean, we can make it whatever thing we want, you know? Does it really have any meaning to it? Not really. You just have to compare it. Right? Compare it with something else. How are we doing so far? Alrighty then. So let's get to the next page. Now for the next page, what you need to do is you need to work on this on. So if you work on back of this page, if you flip it over, you work it on this, so that you could take my notes on it. But I want you to try this on your own on a separate sheet of paper, right? So that you don't like write it on this when I go over it. Then you can write on it. All right. So I'm going to pause the video here and give you about 10 minutes to work on it. You probably don't need all 10 minutes, but I'll pause the video, work on this page, and then we'll come back and we'll go over this and see if you got the right same stuff that I did. All right. So here we go. I'm going to pause it. I'll see you back at 10:20. All right, let's go over this. Example problem, calculating potential energy values. So I think it's important to understand that, first of all, here are some. So gravity, right, and spring. So these are the two equations we should use depending on the situation, right? So here, let 2 kilogram, right, go from negative 10 meters to negative 40 meters. So here, my YA happens to be negative 10 meters, and my YB happens to be negative 40 meters. Okay? So let's calculate what's going on at potential energy gravitation at point A. Okay? And that is simply just MGYA. And that is 2 kilograms times 9.8. Notice I put positive 9.8 in there. Times YA, which is negative 10 meters. So that is equal to, if you work it out, then you get negative 196 joules. Okay. Then it asks to calculate find the potential energy at point B, which is YB. So mgyb. So here, we get 2 kilograms times 9.8 meters per second squared times YB is negative 40. And that, if you work it out, comes out to negative 784 joules. Then it asks, find the change in potential energy going from A to B, right? So it is UB minus UA. So what is UB? UB is negative 784 minus UA, which is negative 196. So if you work that out, you're going to get negative 588 joules. That means that's how much energy was lost. Okay, that's how much energy was lost. Here, from UB to UA, right? So simply UA minus UB, right? Therefore, UB, which is UA, which is negative 196 joules, right? Minus UB, which is negative 784. So that comes out to positive 588 joules, which means that's how much potential energy it gained moving from B to A. Okay, so when you're moving from B to A, you gain that much potential energy. But if you go from A to B, you lose that much potential energy. Okay? Alrighty. Now let's take a look at number 2. So here, in figure above, let 4 kilograms, so this is 4 kilogram mass, and then Y1. At this position, this is 100 meters. Right? So this is positive 100 meters is my Y1. And at Y2, this is positive 120, right? Then at E, this will be Y3, I guess, right? This will be Y3, okay? But I gotta know what this height is, right? I gotta know what this height is. And this height, H, can be calculated saying, well, this is the opposite of my hypotenuse D, but my hypotenuse D happens to be 12.5 meters, right? So H is equal to, right, D sine theta. So my H is equal to 12.5 times sine of, this is 40 degrees, right? This is 40 degrees. So sine of 40 degrees. So if you work that out, your H comes out to, right, 8.03 meters. So your Y3 happens to be 108.3 meters. Positive, of course. Okay? Because this will be 100, 100 plus 8.3 is 103.3. All right, so now we have everything all labeled out nicely. Let's take a look at what's going on at UGA. Right? Well, potential energy gravitation at point A is right here, which is at Y2, right? So MGY2 is what we have to figure out. And that is equal to 4 times 9.8 times 120. And if you work that out with your calculator, you get positive 4704 joules. Potential energy gravitation at point B, the height doesn't change. It's the same height as A. Therefore, it's the same thing. This is positive 4704 joules. That was easy. However, at point C, the height is y1, right? So mgy1, and that is equal to 4 times 9.8 times 100, and that comes out to positive 3920 joules. And then at D, the height doesn't change again from C to D. Therefore, my height stays at 100. So that remains at 3920 joules for potential energy gravitation at D. However, at E, this is mgy3, and that is equal to 4 times 9.8 times 108.3. And if you work that out, you're going to get positive 4234.8 joules. I guess this should be 0.03, sorry. It should also be 0.03. Sorry. So I don't know if that's correct. Let me recalculate that. So 4 times 9.8 times 108.03. Yeah, that's yeah, it's correct with 0.3 in there. Okay. All right. Good. Then now let's answer these questions. Okay. So here we go. So here I have UA to UB. So that is UB, right, minus UA, right? So that's easy, right? So UB minus UA, and that is simply 0, right? So because it's 4704 minus 4704, right? That's easy. Here, this is my UD minus UB, right? And that is equal to 3920 minus 4704, So that comes out to negative 784 joules. That means it lost potential energy, right? So potential energy lost. And then for this, it is UE, right, minus UD, right? So that is equal to 4234.8 minus UD 3920, and this comes out to positive 314.8 joules. Right? That means potential energy gained, right? Okay. Alrighty. So let me see if you guys can do the next page on your own, and I'll give you some time, and I'll pause it again. I'll pause it so that you guys can work on it and see if you can do this. I'll see you back here in 11:42ish. So number 3, now we're going to be working with springs here. So it's probably a good idea to have the right equation for the springs. And springs, of course, is 1/2, right? Kx squared is what we should be using for springs, okay? Now, for example, in this case, we're going to use, this is our equilibrium position, right, where x is equal to 0. And then this would be our position when spring is stretched to 1/2 meter. And then we're going to make this one, spring is stretched to 1 meter. Okay? So obviously, like the US at 0, the potential energy of spring at 0 is obviously 0 joules. So that's pretty easy, right? But what about spring at 0.5? Well, that is 1/2 times K, right? We'll call this like x1, and we'll call this x2, and we'll call this x0, so that we have some kind of a distinction here. So x1, right, squared. Therefore, 1/2 times K, which is 30 newtons per meter, times 0.5 squared is what we should have. And if you work that out, I think you'll get something like positive 3.75 joules. Boom. And of course, here we have 1/2 K times x2, right, squared. Therefore, 1/2 times 30 times 1.0 squared, so we'll get positive 15 joules. Right? Good. So if we were to look at the change in potential energy from 0 to 0.5 meters, right, and that is U at 0.5, right, U1 minus, right, minus U0, right? Therefore, this is equal to then, right? This is equal to 3.75 minus 0 is what we have. Therefore, this will be just positive 3.75 joules or that. So this is how much potential energy is gained, right? Because it's positive. Right? Now let's take a look at potential energy from 1 meter to 5 meters. 1 meter to 0.5 meters. So that is U at 2, right, minus, I'm sorry, U at 1, sorry, minus U at 2, right? Therefore, we have U at 1, which is 3.75 minus U at 2, which is 15. So here I have negative 11.25 joules, which means this is how much potential energy is lost, right? Okay. All right. So here, let's think about that 4-kilogram mass hang on a spring that has spring constant of 40 newtons per meter, right? Calculate the individual spring and gravitational potential energy values and the change in potential energy for the positions given, okay? So I guess here, this location here is, right? So here, nota bene, right? At this point, U spring is equal to 0 because it hasn't been compressed or stretched, right? However, U gravitation is equal to mg, right? Y, and this Y asterisk. Y asterisk here is, since this is 0, this is 1 meter, and this is stretched to 0.25, so here is Y asterisk, and that is 1.25 meters. So here you can say 4 times 9.8 times, right, 1.25. And that comes out to positive 49 joules at this point. Okay? All right. So let's take a look at potential energy of spring at point A. Right? So I'm going to do spring potential energy in pink and gravitational potential energy in green, and this would be at point A at blue. Okay? So here, potential energy of spring at point A, USA. So 1/2, right, kx squared. So k, which is 40 times a, xa is 0.25, right, squared. And if you work that out, I think you get positive 1.25 joules. However, gravitational potential energy at point A is m, which is 4 times 9.8 times ya is just 1, which is simply positive 39.2 joules. So the total energy right? So total energy at point A is equal to, right, how much total potential energy do we have? That is simply, right, U spring A plus, sorry, plus UGA, right? And that is 1.25, right, plus 39.2. And that comes out to positive 40.45 joules. And then USB. USB. Here, potential energy spring at point B is simply 1/2 times 40 times 1.25 squared. And if you work that out, you should get positive 31.25 joules. Okay? However, for UGB is just 4 times 9.8 times 0, which is just 0 joules. Well, the total energy at point B is going to be then simply USB plus UGB, which is 31.25 plus 0, and that comes out to just positive 31.25 joules. So how much potential energy change is there from UB to UA, right? So that is UA minus UB, right? That's total energy, potential energy at A minus the total potential energy at B. So that is equal to then, right, positive 40.45 minus 31.25, and we get positive 9.2 joules of energy gained. Okay, so this is potential energy gained. That's it. All right. All right. Your first lecture note for 2021. We'll end it there for today, and I'll see you guys on Wednesday. Have a nice day, everybody.